Good morning, everybody. My name is Tim Tomlanovich. I teach civil engineering technology at NWTC here, and I want to talk to you about concrete. I look forward to seeing all of you on Friday, April 8th. We can teach you how to do a concrete mix design. I apologize, I'm a little under the weather, so I may have to pause it or my voice may crack a little bit here. So with that, I'm going to share my PowerPoint and we'll talk about concrete. Okay, let's see. All right, so concrete. So there's three main ingredients of concrete. We have aggregate, cement, and water. Okay. So a lot of times you hear the word, yeah, I have a cement driveway. That is not correct. So cement is one of the ingredients of concrete. So it's like calling a cake a flour. Flour is in an ingredient. Okay. So let's talk about the first ingredient, aggregate. What is aggregate? Aggregate is the granular materials such as sand, gravel, crushed stone, or blast furnace slag used with cementometing to form hydraulic cement mortar, concrete or mortar. Okay, where does our aggregate come from? So our aggregate comes from our natural bedrock, depending where we are in the United States or in the world. So there's three basic types of bedrock. There's igneous bedrock, sedimentary bedrock, and metamorphic bedrock. So typically, concrete plants, what they'll do is we'll have to mine and blast and crush and to create our aggregates depending on the local source. So here in Green Bay is this is the rock cycle. Let me back up here. The rock cycle basically it's similar to the weather cycle. So volcanic erupts, it creates igneous bedrock, it weathers, it turns into sedimentary. As it gets pushed deeper to lower in the earth, it turns to metamorphic. Metamorphic, it changes and um, rocks types, and then this rechanges its bedrock type. So this takes billions and billions of years to create these different kind of rocks. So a rock cycle. So as I was saying before, depending where we are in the United States or in the state of Wisconsin, they want to use local sources. So here in Door County area, you're using sedimentary rock, which is called dolomite. You know, if you go into the central Wisconsin, it's called, we're using igneous rock. So depending where we are, we want to use our local sources and we want to have certain aggregate properties. Okay, so let's talk about the different kinds of coarse aggregate. So we have two types of aggregate. We have coarse aggregate and we have fine aggregate. So basically, we coarse aggregate is the bigger stuff that is retained on the number 4 sieve. Okay, a number 4 sieve means there's 4 openings per square inch, and then the space between each of the bars is 4.75 millimeters. Okay. Fine aggregate passes the number 4 sieve, but is retained on the number 200 sieve. Again, 200 openings per square inch, and then the space between the bars is 0.075 millimeters. So these are the coarse aggregate and fine aggregate are is the majority of concrete. Okay, it's the backbone of the concrete, just like the bones in our body. Okay. So some coarse aggregate definitions, we have typically gravel. They're mostly rounded faces, is because our glaciers, we were in a glaciated area. The glaciers advanced and retreated several times over 100,000 years. Our latest retreat was about 10,000 years ago. So basically, a glacier acts like a bulldozer and it just pushes it, and then it transports it, and then it rounds the gravel faces because it ripped off the bedrock basically. Okay, they call that physical weathering. So then there's crushed gravel. So because of our rounded faces, it's like marbles. You don't get a lot of friction. So what we want to do is we'll actually crush them to create angular faces so we get a lot of friction. So we call that crushed gravel. Crushed stone is literally we take big boulders and we crush it down into gravel size and we make angular faces. All right, some reason Let's pause in here. There we go. Fine aggregate. So number fine aggregate passes the number 4 sieve and retained on the number 200 sieve. Our natural sand is also very rounded. It just weathers further from the rounded gravel, and it's very rounded. So we have a very rounded sand in our area because of the glaciers. So if we need more friction, we'll make manufactured sand where we'll basically crush the natural sand, or we'll use recycled materials such as blast furnace slag and old concrete. There's something called bank gravel or pit run. This is basically a hodgepodge of everything. So you got to think about those glaciers. They came down and they basically bulldozed, scraped from the bedrock, and this bulldozed all the material. And basically, when the glacier stops and starts retreating, it creates this bank run. So it can be used. As you can see here, there's a lot of rounded material, fine and coarse aggregate in there. So what they can do is they can mine it. They'll wash it through, they'll run it through a gravel pit and run it through certain sieves and clean it up to get the sizes that we need. So then there's something called fines. Don't confuse this with fine aggregate. Fines pass the number 200 sieve. This is why we have a lot of the silt and clay around Green Bay area. So basically, those were deposited in a very calm setting. The glaciers actually trapped water in like a lake setting, and then the fine particles settled on top. So these are very sticky, as you notice when you walk around your clay field, and these cause a lot of problems. So what this does, these silt and clays, they'll actually coat the outside of the aggregates, and then the cement doesn't want to bond to the aggregate. It's binding to the fines, and then it peels apart. It doesn't work very well. So we want to control a lot of our silt and clay or fines passing the number 200 sieve. So we had different kinds of um, aggregate types. So typically we're in the normal weight aggregates. Our dolomite is 75 pounds to 110 pounds per cubic foot. Heavyweight is more in the iron ore minerals, and then lightweight is more of the igneous rocks, very porous rocks. We can use those if we need to reduce the loads on our structure. So let's talk about aggregate properties. Aggregate properties, so these are good properties we want. We want soundness. Because of our climate, water loves, we have a lot of water, and then when it gets cold in the winter, water loves to freeze, and that can actually break apart our aggregates. So we want a good sound aggregate that can resist the freeze thaw of the aggregate, because aggregates have microscopic pores that we can't see. That water will actually get inside of the aggregate, and then when it freezes, it'll break it apart. Another good one is particle strength. That basically we can put the load on it, either tires with a concrete pavement or foundation of the tallest building in the world, that basically when that load comes on, it doesn't break. Okay. Toughness is another one, who is to withstand abrasion. So I want you to think about tires going over a highway. Over time, that abrades the highway, especially when we plow our roads. That steel plow is scraping across the road, and that's abrading the aggregate, and it can actually deteriorate it, which makes it too smooth, and then we could also have, cause very slippery roads and hydroplaning. Shear strength is another thing. We want those aggregates to interlock. That's why we create angular aggregates. So we want rough surfaces, flat broken faces. So basically we have a very good combination of coarse aggregate and fine aggregate all mixed together. So we have the nice angular aggregate to aggregate interface touching, so we can transfer the load through the aggregate. So just like strong bones in our body, we want to transfer the load to the aggregate. Okay, so the load, our weight is transferred through our bones. So if we didn't have strong bones, we would deteriorate. Let's talk about some bad aggregate properties, or deleterious properties. So we have friable particles that's easily crumbled. P200, we don't want a lot of P200. I explained that. We don't want it to coat the particles. We want the cement to bond. And we have soft particles, which break under ease under loading. So friable particles and soft particles are similar, right? Friable particles we can actually crumble in our hand, and those do exist in bedrock. Soft particles, we probably can't break them with our hand, but they'll break under very light loads. We also have lightweight pieces, low specific gravity. Um, this causes, coal, chert. This cause actually they like to absorb a lot of water, and we causes the freeze thaws, and they call pop outs. So if you look at the sidewalk or any of our aggregates, sometimes you see it there, and you see these pop outs. It's because water gets in there, freezes, and it literally pops off. And then we have organic impurities, especially in our mixing water or possibly in the bedrock. It causes issues curing this cement. Reactive aggregates. So this is a very uh, an issue here in northeast Wisconsin. Is due to our dolomite bedrock. There's chemicals in that bedrock that actually react with the Portland cement that actually causes a reaction and wants to react and expand the concrete, the aggregates. So it actually very slowly deteriorates the concrete. So when you look at, I just actually drove by the dam in O'Connell Falls there. When you look at it, you see this similar spider cracking, and you see this white material around the cracking. That's called silica reactive aggregates. That's what's going on there. So it's slowly deteriorating the aggregates, and it's breaking apart, so that won't last as long. And then the last one is hydrophilic um, aggregate, which actually attracts water, not um, pholic, hydrophobia. It repels water. We're afraid of it. It wants to attract it. This is issue especially in asphalt. So we have the same properties in asphalt pavement. Um, if the water is being attracted and coating the aggregates, the binder, which is what is the glue in asphalt pavements, will actually bind to the water, not the aggregate, and we have very weak pavements. And this can also be an issue with um, cement and curing the cement too. So let's talk about our different aggregate moisture conditions. So I talk about aggregates have little pores, okay? So basically aggregates, if we put them in the oven and we dry them overnight, we call it oven dry, all right? There's no water outside or inside the pores, okay? So now if we take that oven dry aggregate and we put it in a bucket of water and let it sit there for a little bit, all the internal pores and the external pores here will fill up with water, okay? And then what we'll do is we'll take that out and we'll pat it dry. So basically, there's no surface water, but all the pores are filled. That's saturated surface dry, okay? And we'll talk about this soon. And then there's wet. So basically, that's saying that all the pores are filled with water, plus there's excess water on the outside of the aggregate. So there's three aggregate moisture conditions or water contents: oven dry, saturated surface dry, and wet. Okay. All right, so now let's talk about the last two ingredients, the cement and water. Okay, so Portland cement concrete. So Portland cement, Portland is a brand name. Um, it's capital P is it basically this is what you can buy in a store. Portland cement concrete, PCC is a mixture of two main components. So I said there's three ingredients: aggregate, cement, water. So aggregate is the one main component, and paste is the second main component. Paste consists of the cement and the water. So the paste is the glue that binds the aggregate together. So paste again is cement and water. And also in that we have entrapped air and entrained air, okay? As just like you mix a cake mixture or mix anything, entrapped air, tiny air bubbles get entrapped in it. Okay, and then what we'll do is I'll talk about entrained air to help resist freeze thaw a little bit later. So the quality of the concrete depends greatly on the quality of the paste. Each particle should be coated with paste, and all the spaces between the particles, the aggregates, should be filled with paste. So we want a very good, solid, thoroughly mixed paste, coating all the aggregates. Okay. Calcium silicates in Portland cement reacts with water, so they call that hydration. That is a exothermic reaction. It creates heat, and that's what causes the concrete to cure. They call it curing. So without the water, we won't have concrete because we need to cure the cement. Okay, how do we make Portland cement? Literally, Portland cement is also made from bedrock, from minerals that are found in bedrock and soils: calcium, iron, silica, alumina, and sulfate. Those are actually found in bedrock types. Okay. And then what they are doing is they're actually, these raw materials are thrown into what they call as a kiln, and it's rotated and it's heated up to 2600 to 3000 degrees Fahrenheit. And what happens is clinker is formed, and then clinker is ground, and that's where we get the gray cement. And then what we have to do is they have to put gypsum in it to keep it from curing too fast, because once water hits cement, it starts curing and it creates heat. But if we can't have that reaction happen too fast, otherwise we won't have time to work with the concrete. So Portland cement physical properties: fineness, strength, heat of hydration, and setting time. So the more fine we make it, literally fineness is like grinding it, we can create a faster reaction. We need strength of it. Sometimes we may need the heat of hydration. We may just slow that down. And then setting time. How fast will that concrete cure so we can actually start walking on the concrete and finishing it? Sometimes we need to speed it up. Sometimes we need to slow it down. Okay. So there's 5 different types of Portland cement types. So type 1 is normal, and type 2 is moderate sulfate resistance. Typically, when you go to Home Depot or Menards, you can see a type 1 slash type 2 Portland cement in a bag. Okay. Type 3 is a high early strength. So literally what they do is they grind that finer. And why we use a high early strength? Typically, concrete will gain its full desired strength, design strength, in 28 days. But sometimes we need to construct that building faster. We need to get loads on there as early as 7 days. So if we use a high early, it'll hydrate faster and cure faster, and we can use a high early strength. And then type 4 is low heat of hydration. So it's a complete opposite. So when you look at the Hoover Dam, that's a very mass amount of concrete. So the more massive concrete we have, the more cement, the more heat we're creating because of the hydration of the cement. If it cures too fast and we create too much heat, we get cracking of the concrete. That's not a good thing. So what they did is actually run air conditioning vents and cold water through that entire dam to keep that hydration slowing down. And what they also did too is they can use a type 4 that actually reduces the rate of hydration in there. Okay, so there's a type 4. And then a type 5 is high sulfate resistant. So when you look at a wastewater treatment plant or wastewater pipes that are made out of concrete, due to the sulfuric acid, it'll actually degrade the concrete over time. So we need to resist that degradation from the sulfate chemicals. Okay. So again, typically our normal stuff is type 1, type 2, and then we have these special ones that they can make. All right, let's talk about the mixing water. Okay, so mixing water, so typically there is reinforcement in mixing water. Chloride, our city water has chloride in it that can contribute to steel corrosion. Sulfate can cause expansive reactions. Remember me talking about the silica alkali reaction due to the chemicals in the bedrock, and the sulfates in the water can cause that. Alkalis, we can affect the setting time and strength. And then organics can really cause, I've seen very multiple issues of organics in the mixing water. So it's important that we understand where our mixing water is coming from. So typically city tap water is okay, unless, steel corrosion is a major concern. There's usually not a lot of chlorides in the water that can cause this, but sometimes we may have to watch it. Okay. All right, now let's go back to that entrapped air and entrained air. So if we look at a mix, there's typically 2 to 3% entrapped air in concrete just due to the natural mixing process. Okay. All right. So concrete is not impermeable. Okay. So water will infiltrate into concrete, especially on your foundation walls. So what we want to do when water gets into concrete and it freezes, it expands, so it'll break apart the concrete. So what we do is we actually add entrained air. Okay. So entrained air, my lights just went out in the classroom, but we'll just keep going. Um, Entrained air is actually, it's a chemical, it's a liquid, and actually when we mix it, will actually induce microscopic air bubbles into the concrete to give room for that water to expand and contract without causing the concrete to break up. Okay. So let's talk about water cement ratio. So this is the paste, right? Water and cement, okay? So those who've made pancakes before, so if we have too much water in a pancake, it's really too runny. And if we have too little, it's a really bulky and the pancake batter doesn't get mixed very well. So remember, our goal is to completely coat each aggregate and fill the space between aggregate particles, the coarse and the fine aggregates, okay? And another goal is that we want to make sure there's just enough water to completely hydrate the cement. We don't want too little and we want too much, because if we have too much water, that water just sits in there because the cement doesn't need it to hydrate. So it's called a water cement ratio. Okay. So we don't want to make the pancake too runny, or we don't want to make it too dry. Okay. So what happens is, as we keep adding more water, our water cement ratio goes up and it makes it more runny. And if you kind of look at this picture here, see, we get our cement particles get further apart and then we have weaker concrete. Okay. So we want to reduce the water cement ratio as best as we can. My lights aren't going to turn back on in the classroom because of the sensors, but oh well. It increases compressive strength. Um, the less water cement ratio, we have better permeability. Water can't get through it. It can resist the weathering. Better bond to reinforcement, less volume change, and then reduces shrinkage cracking. So if we can reduce our water cement ratio, but still have just enough to properly hydrate that cement, we'll have a good quality, long lasting concrete. Okay, so. All right, so going back to the moisture conditions, okay, how does the water cement ratio change of each aggregate moisture conditions? Okay, so say I have 100 pounds of water I need to hydrate that cement, okay? And if I put oven dry in my mix, the first thing that's going to happen is that water's going to suck into the aggregate, okay? So that means we're not going to have enough water to hydrate our cement, so our water cement ratio actually goes down, okay? So now if we go to the saturated surface dry condition, all right, so that means all the pores are filled. We have 100 pounds of water to hydrate our mono cement. Our water cement ratio will not change, will it? Because our aggregates are full. Okay. Now, if we have a wet aggregate, so say on a summer day, it's raining out, it rains for 24 hours and the aggregate pile gets wet, and I don't adjust how much water I weigh, I'm actually going to increase my water cement ratio because I have this extra mixed water in here, don't I? This extra water outside the aggregate is part of the mixed water, so I'm actually diluting my pancake mix and I'm making the concrete weaker. So this is very important, and when we do mix design, is that we understand our aggregate conditions, okay? Because we need that water cement ratio designed perfectly. So understanding that is key. Okay. So now let's go to mixing PCC. So when a truck arrives on site, typically 70 to 100 revolutions at mixing speed. You hear that motor revving? They want to make sure that concrete is mixed thoroughly. Okay. The concrete should be discharged before exceeding 300 revolutions of that drum. And then as soon as water hits that um, cement, they have an hour and a half to discharge it. Okay. Uniform distribution of ingredients. So sometimes the concrete will come out really chunky. They didn't mix it long enough, so they may have to mix it higher at mixing speed. And then a lot of times if there's worn coated blades, it doesn't work well, doesn't mix well, and then proper amount of revolutions. Okay. All right. So I want to just go back to this slide. So how they mix concrete at a plant is typically what they'll do is they'll add about half of their mixing water, and then they'll add the aggregates into it, and they'll actually mix the aggregates with the mixing water, so that gives it time for the aggregates to suck up any of that water that that needs to be sucked up, and then they'll add the remaining ingredients, and that way the concrete truck driver can add or subtract, if he needs more water or less water due to the aggregate condition. So I wanted to verify. So that's why it's important that you mix most of your mixing water with the aggregate before you even add the cement. Okay. All right. So sometimes, like you say, if it gets to on the job site and it's really chunky, if we don't exceed the water cement ratio, there's a thing that we call measuring a slump. It doesn't exceed the drum revolutions. We can always add water to help facilitate getting that water discharged or that cement concrete discharged. Let's talk about handling PCC. All right. So when it gets from the truck into the foundation forms and walls and footings and pavements, there's delays that can cause it to dry. We can have early stiffening out and drying. We can have segregation. So everybody's seen this. They call this honeycombing. You know, Obviously water can penetrate through that very easily, right? The reinforcement is exposed, so we can get corrosion due to the water, groundwater. Okay. Some more things, placement lines. Honeycombing, placement lines, sand streaks, bug holes. So this is not very well placed consolidated concrete. So it's another skill for those contractors and those workers out there. They're properly placing and consolidating that concrete properly. Okay. So we want to get the concrete between all the reinforcement bars. They're using this is called a concrete vibrator. They use it to, make sure it's consolidated properly. They're placing it. They're not using this concrete vibrator to move the concrete. So it's very important that it's being, one is they're calling this placing the concrete and then consolidating concrete with this piece of equipment right here. Okay. So now after they they place it, they consolidate it, they finish it off. Now we got to cure it. Okay, why do we need to cure concrete? Well, one, to keep that exothermal reaction going is that we need to prevent moisture loss. So on a very hot sunny day, it'll evaporate. So what they'll do is when it cures, they call it setting. When the concrete sets is usually when you can walk on the concrete. Is we got to keep moisture on it. So like in a concrete bridge, they'll put wet burlap over it. They'll keep it moist. Okay, and then it needs time. There always needs time. Okay, so concrete will gain 2/3 of its strength in the first 7 days, and then the full strength in 28 days. So time. So we need to keep moisture in it and we need time. Also, we need temperature. Okay, we can't let it freeze and we don't want it to get too hot. So we want to keep it cool and we want to keep it in a medium temperature. Okay, that's the objectives of curing to get quality concrete. All right, so here's different methods. Okay, so sometimes you see them spray that curing compound on it when they're doing a sidewalk or a road. That helps keep the moisture in. Okay. So in the winter, they'll steam cure it. They'll put insulating blankets on it. Usually they do that for at least 7 days, in the winter, just to make sure that concrete has a chance to cure and the heat and the moisture. Okay. So hot weather difficulties. So the key is, so concrete will cure a lot faster, right? So the idea is, oh, just add more water to the concrete truck and remix it, right? But what are we doing when we do that? We're actually increasing the water cement ratio, so we can also cause shrinkage, reduce quality of concrete. So there's actually we can use actually retarders. They're actually call it an admixture that can actually slow down that hydration to help with that. So hot weather, we deal with a lot of this. So the last thing you want to do is add water. So either you want to use a low hydration cement or add an admixture to help control the cure rate of that concrete. So basically what they'll do is they'll add ice, they'll use cold water, use shady equipment, and then again, like I said, retarding admixtures. Cold weather, we don't want it to freeze. So believe it or not, below a temperature of 14 degrees, the cement reaction stops. And then once it stops, it will restart, but it will not be 100%. So you've basically ruined the concrete. You ruined the reaction. So that concrete quality is not there anymore. So it's very key in the very first, I'd say, 8 hours is that that concrete does not freeze and it continues to be cured for at least 3 to 7 more days to make sure that that hydration continues with heat, time, and moisture. Okay. So again, we'll warm ingredients, we'll heat forms, we'll use blankets, and we also use accelerator or high early mix to help increase the hydration of that cement to make the concrete. All right. So that's all I have. So again, I look forward to seeing you I look forward to seeing you on Friday, April 8th and talk about mix design. Thank you so much for your time, and we'll talk more about concrete soon. Take care.